He's our honored guest, and everybody, I think, knows Dr. Lobo, the machine man, we call him that actually. So, Dr. Lobo is consultant nephrologist, KEM Hospital, Pune, MD, Medicine, DNB Nephrology. Publications, he has had around 23 original articles and 12 textbook chapters. He is a member of Indian Society of Nephrology, Indian Society of Critical Care Medicine, and West Zone chapter of ISN. I think this is again an old CV. So he is always a permanent fixture at most of the dialysis conferences and knows the machines in and out. And all postgraduates of nephrology, before they go for the exam, should definitely have a session with Dr. Lobo. And I think he keeps on getting calls from all of us, even after we pass our degrees, because he is the go-to man if you run into any sort of problems with tubings, pipes, machines, or filters. So over to you, Dr. Lobo. He has a special interest in hemodialysis, biopsy, and TMA as well, and I'm sure you have heard of his lab, which is doing phenomenal work. Over to you, Dr. Lobo.
I just want to add one sentence. He is only a nephrologist. He can actually, dismantle a machine and then reassemble. And he's actually in a combination of a technician, nephrologist, and the manufacturer also. Over to you, sir.
Thank you, Dr. Manisha and Dr. Swarnalatha. I'm overwhelmed by the introduction you have both given. I hope I can live up to it. And thank you also so much for inviting me. It's a pleasure to come to Hyderabad, where I've got so many friends in the nephrology community. So you asked me to demystify dialysis technology. Let's see what I can do in the course of the next 35 minutes or so. So I will confine myself to the two machines that I'm most familiar with some references to others, that is the Alton's UltraTouch 1000 and Fresenius 4008. So this is what the Indian Society of Nephrology says about machines, that any dialysis machine being used needs to be certified and needs to conform to standards by an appropriate authority, which is the FDA, and in Europe it would be the ISO, which has more stringent guidelines with regard to machines. The machines that we typically use in India, the other machines are slowly coming in, are what are called single pass machines. That is, the dialysate comes from the machine, goes to the dialyzer, back to the machine, and goes to the drain. And they are also called negative pressure machines, as opposed to many years ago the Travenol was a positive pressure machine. So if you were to look at a machine, ISO calls a dialysis machine a class 1 device. That means that at no stage should the body of the machine conduct an electric current, because the blood lines could take that electric current directly to the patient. So it does this with the help of this earthing connection over here. So if you open your machine, you will find this green and yellow wire at the back, which is connected to the body of the machine and which connects to the earth socket of your mains, which means that a dialysis machine must always be plugged into an earthed supply. Unlike cardiac monitors or ventilators, which take about 500 milliamps of current, a dialysis machine will take something like 9 to 10 amps of current. So it needs to have a 15 amp voltage supply. Now, this is the most commonly used machine, I think, in India these days. Fresenius is 4008S machine. It's an ideal machine in many ways. The design of this machine is pretty good. At the top of the machine, you have the microprocessor unit and an LCD display. Below that, what you have here is the blood pump with the various pressure port monitors. There is a lot of talk about pressure since this morning. And at the back of the machine, in the corresponding area, you have the machine's power supply. And in the base of the machine, you have the hydraulic unit. Now, this is actually my favorite machine, which I have opened from the back. This is Alton's UltraTouch 1000. But where Fresenius scores over UltraTouch is in this design. If you see the UltraTouch, the main power supply enters through the base of the machine, and the hydraulic unit is here above it when closed. So should there be a leak in the hydraulics, you could have water or dialysate dripping down onto your main power supply board. It shorts, and then you have a problem. The other part about Fresenius, which is superior, this is the top portion. The motherboard is a horizontal motherboard placed here, and all the function cards are stuck vertically into it. In contrast, in Alton's, this is what you have. You have a vertical motherboard with the cards stuck horizontally. So should this machine have a bumpy ride when it is being transported from one place to another, these cards will work themselves loose and your machine may not start in a different location. We can think of the dialyzer as something of an interface. So you have a blood circuit here on the right hand side, which consists of bringing the blood from the patient with a blood pump and returning it to the patient without producing coagulation or hemolysis along the way. And within the machine, you have the preparation of the dialysate, which is also delivered to the dialyzer and then taken back by the machine to drain. So the ISN says that any dialysis machine must have certain mandatory requirements. So it must be able to have, the blood pump must be able to deliver blood flow at about up to 400 ml per minute. As I said, it needs to be anticoagulated. It should have arterial and venous pressure monitors. It should not allow an air embolism, so there should be an air bubble detector. It must deliver dialysate of the right composition, that means chemical composition and temperature at 300 to 500 ml per minute or more. It must prevent blood leak in the case of a dialyzer rupture. It should be detected, and it should produce an accurate ultrafiltration. So how does the machine do all these things? So there are some optional features, and they are present on a good many machines available today, but they won't be the subject of my talk, and I know at least that there's a talk coming up on hemodiafiltration after this. But if you don't have these, you can still do good dialysis. So what does the machine do? The blood pump of our dialysis, we've just heard that the ECMO pump is a centrifugal pump. Now, the centrifugal pump means that the blood enters the body, the housing of the pump. In contrast to that, our machines use a roller pump in which there are 2 or 3 rollers rotating, which squeeze the pump segment of the blood tubing. That creates a vacuum, and as the roller moves forward, that vacuum sucks blood and fills up with blood coming from the vascular axis. The amount of blood flow is a function of the volume of the pump segment and the rotational speed of the motor. And there is a Hall effect sensor which feeds back to adjust the rotational speed of the motor. So this is the back of the blood pump module. This is the motor here. This is the drive card, and the green, white and brown wire which feeds into this is the Hall effect sensor. So Hall effect says that an electric current will be produced when there is a something rotating in a magnetic field. So as the motor rotates, its shaft will develop an electric current, and that's picked up, and that electric current is proportional to the speed of rotation. So the Hall effect sensor will feed this to the drive card. This will be amplified, converted into a digital signal, go to the microprocessor, and then the microprocessor will feed back a digital signal which has to again be converted to an analog signal to drive the pump. And you can also see this tubing inside, which connects to the arterial pressure port and then to a strain gauge sensor within the machine. Now this is what the roller pump looks like. There are 2 rollers here, these brown things, and the rollers are maintained at a fixed distance from the stator by the tension in a spring over here. In most of our dialysis circuits, our tubings have an occlusion diameter of about 6.4 mm. The 5008 uses dedicated pump segments which have an occlusion diameter of 8 millimeters. So if the tubing set needs to be, the machine pump needs to be adjusted, the roller stator distance needs to be adjusted to the pump segment that we are using, and it can be done with the help of this nut here. If you tighten it, you increase the tension in the spring, and that pushes the rollers further apart, reducing the occlusion diameter. If you turn it anti-clockwise, it reduces the tension and brings the roller segments further, increasing the occlusion diameter. And failure to choose the right occlusion diameter can result in a lot of undesirable things, as you can see, to the blood. This is one of the things that happens when your occlusion diameter doesn't match. The tubing gets stretched, it gets converted from a circular cross section to an elliptical one. And as we know, an ellipse has 2 axes. Now, what is the consequence of this is that the cross-sectional area will decrease in proportion to the ratio of the lengths of the axis. So greater the ellipse is long axis to short axis ratio, less will be the cross-sectional area. And since cross-sectional area into rotation into velocity of the pump is equal to blood flow, as the tubing gets stretched, it actually will deliver a lower blood flow. And you can see this if you
connect your arterial pressure port. This is what happens to the pressures in our blood tubing. The pressure is at its most negative just before the blood pump and at its most positive immediately after the blood pump. So there is an acute transition from a negative pressure, as has been said earlier, to a positive pressure, and then it gradually dips down, being the lowest where the blood enters the venous axis. Now, this is what the machine also has on the return side. It has a venous pressure port here, and these two arrows which allow us to adjust the level of blood in the venous bubble chamber. It has an ultrasonic air detector over here, which is based on the principle that sound travels fastest in solids or in semi-solids blood, which is actually a colloidal solution, a little slower in liquids and slowest in air. So on either side of this air detector, we have a piezoelectric crystal which generates ultrasound waves on one side and detects the velocity of the wave passing through the blood column on the other side. And should the velocity fall below a threshold which we set on the machine, then it will detect that there is an air-blood mixture. It will shut off the blood pump and it will clamp the return line at this line clamp. Now, this is what it looks like from the inside. So this is the venous circuit card. You can see we put a small transducer protector on the outside. There is also a transducer protector on the inside of the venous port which protects this strain gauge sensor over here. If blood were to cross our external transducer protector, this transducer protector would still protect our transducer which is located here, but then we would have to change the internal protector before reusing the machine. And you can see these two ports over here, these are from the air detector. So this is the feedback of the air detector being given to the venous control card, and this is the motor which moves the line clamp lever. Now here you can see that the air detector alarm is alarming. There's a red light flashing at the top of the machine, although the tubing segment appears to be nicely full of saline. So it shouldn't have given the alarm. Why does that happen? It happens because there is a wide variety of blood sets available for sale, and there is a wide variability. There isn't a standardization of blood sets. So when you change your blood set, if the newer blood set is narrower than the one being previously used, then a column of air might form between the detecting crystal of the air detector and the blood tubing segment, and that will give a false air alarm. To take care of that, we need to calibrate the air detector each time that we change our blood sets. You do that with the help of this jumper J2 over here. This blue has to be moved from the 1-2 position to the 2-3 position, and then these two potentiometers P1 and P2 are to be turned progressively anti-clockwise until this LED here, LED 1 just goes off, and then half a turn clockwise till it comes on again, and similarly for LED 2 and potentiometer 2. So much for our blood circuit. Let's look at what happens inside the machine. The machine needs to take in our treated water. It needs to heat it, de-aerate it, remove air bubbles which could cause a problem, and it needs to mix it with the acid concentrate which contains most of the electrolytes and the bicarbonate concentrate, deliver it to the dialyzer, check its composition, make sure that it's delivering the right thing. Then it needs to transfer it back to the machine, making sure that no blood leak has occurred in the dialyzer. If you have a service card, you can place it into the slot on your 5008 machine, and it will open up this diagram for you on the machine screen. So these are the hydraulics of the 5008, and you can then, by just touching any of the components here, you can see whether it is functioning or malfunctioning. Okay, so the machine must heat up the incoming water, which it does with the help of this heater. And this heater is what consumes most of the power in a dialysis machine. It's 1500 watts, which means it takes about 7 amps of current. And so if you place a 5 amp plug to your dialysis machine, it's going to throw your circuit breaker or blow the fuse. This black knob over here is the adjustment of the inlet water pressure. Remember that while you may increase the pressure by turning the knob clockwise, it cannot raise the pressure above that of the line pressure. So dialysis machine manufacturers will tell you what is the minimum pressure that the machine must receive. It's about 10 bar, TSI or 0.7 bar the Alton machines, it's about 1 to 1.3 bars for Fresenius machines and 1.5 to 2 bars for the Gambro AK series machines. So your line pressure must be at least 2 bars of pressure, and then you can adjust the pressure coming to the machine with the help of the knob. So there are 4 pressure monitoring points, these red knobs over here, at which points we can measure the pressure within the hydraulics of the machine. The lowest one, this is valve V41, which when the machine is switched on, this valve closes so that the water, instead of going to overflow, is delivered to the degassing pump, and the pressure of the incoming water can be measured here and adjusted with the help of this knob. This is a negative pressure, which is the degassing pressure, and it has to be about -8 to 1.05 to -1.5 bar. This is the balancing chamber loading pressure, which is on the positive side of the degassing pump. Incidentally, this is the degassing pump, and this is the dialysate flow pump. And this is the dialysate flow pressure, which has to be about 0.8 to 0.9 bars. So the degassing pressure is negative, all the other pressure points are positive. And we are using geared pumps in a dialysis machine, and this is what the gears look like if you were to open up a gear head. What gearing does is it converts the rotation per minute of the motor to a torque which can move a load of water. So it adapts the motor to the load, and it functions as what is known as a torque amplifier. It also reduces the vibration that would otherwise take place if one were trying to move a load without a gear head and using the high RPM of the motor. It also allows variable flows. Now this is the dialysis menu of the 4008 machine. It can have flows of 300 ml per minute, 500 ml per minute, or 800 ml per minute. If you have a 5008 machine, you can adjust the flows all the way from 100 ml per minute to 1000 ml per minute in increments of 100. Now this is something that you will see this warning on the machine often, flow alarm. Why does this happen? 4 possible reasons. This is the Diasafe Plus, or the endotoxin filter, which is placed by Fresenius in the flow path of the dialysate. Now this is the path which offers the highest resistance. It has a pore size of 0.05 microns, and it operates in cross flow mode. So if the machine has not been periodically rinsed and not been decalcified with heated citric acid at least once in a day, calcium carbonate precipitates will form in the Diasafe filter. Over a period of time, say the life of the filter, which Fresenius says is 400 hours, or a time period of 3 months if less than 400 hours by that time, in any case the filter pores may get clogged. But it may happen much faster if precipitates form, and in that case a flow alarm signal will be seen. Another cause is that the gears will tend to wear down with time. When the gears wear down, the machine will give a flow alarm, but this flow alarm can be taken care of by increasing the rotations per minute, and that is done by increasing the digital to analog conversion digits on the calibration flow menu. Finally, our motors are brushed motors. They work with the help, the electricity is delivered to the rotor with the help of these carbon brushes. And as you can see, over a period of time, because of the friction between the rotor and the carbon brushes, the carbon brush will get shaved down and it will lose some length. So this is a new brush, and this is a brush which has been in use for some time. So over a period of time, the brush's length will fall to an extent where it no longer makes contact with the rotor, and at that point of time a flow alarm will occur and the brushes will need to be changed. Otherwise, no matter what adjustments are made in the calibration menu, you will not get rid of the flow alarm. So this is what the inside of it looks like. The 24-volt DC supply is delivered to the motor by these 2 wires, the red and the black, and on each of these posts, within these two brass housings, we place these carbon brushes, and they make contact. So the wire is connected here, and there's a spring that holds the carbon brush in place, and it makes contact with the armature of the motor here. As the motor rotates, as I said, it will wear down the brush in this fashion. So after about 18,000 hours, the degassing motors pump, either the brushes will have to be changed or the motor itself will have to be changed, and after 22,000 hours, the flow pump will usually meet with the same fate. Right. So preparation of dialysate, I said diluting concentrated solutions. One of them, the acid concentrate, contains all the electrolytes except bicarbonate, and the base component contains sodium bicarbonate, which is the buffer in dialysate. And if we set a dialysate sodium of around 140, as you can see, all the electrolytes are coming except bicarbonate, and some of the chloride is coming from the acid concentrate. So the final sodium of 140, 82 millimoles come from the acid concentrate and about 58 millimoles from the bicarbonate concentrate. This depends, of course, on different ratios or proportions which are used. The most common formula used in India is the Drake bicarbonate formula, which mixes 1 part of acid, 1.83 parts of bicarbonate, and 34 parts of water. But there's also the Cobb formula and the Fresenius formula which can be chosen. If you have a now in most of the machines one has to factory change the settings, but when it comes to the 5008, in the setup menu we can feed in any number of dialysate concentrates, and all you have to do then is to choose the one you want to use, and the machine will display what it will the dialysate will contain, and this can be matched with the label on the concentrate. Right. So the concentrate may be picked up in various different ways: by piston cylinder pumps in the Alton machines, by diaphragm pumps in the Fresenius system, and by peristaltic roller pumps in the B. Brown machine. Now, if you can see here, the pump on the left hand side is rotating about twice as fast as the one on the right. So the one on the left is the bicarbonate pump. It has to deliver 1.8 times as much bicarbonate as the acid concentrate. So in our dialysate menu, what we are allowed to set is to prescribe the prescribed sodium for the treatment, the bicarbonate, the temperature, and the dialysate flow. When we choose a bicarbonate value which says the default says plus minus 0, the default value is about 32 millimoles per liter of bicarbonate. If we increase the sodium from 136 to 140, leaving the bicarbonate at 32, then all the other electrolytes coming from the acid concentrate will increase slightly. So potassium goes from 2.2 to 2.23, calcium to 1.52, not really significant, but it can change. If on the other hand we choose to increase both the sodium and the bicarbonate, the additional sodium is taken from the B concentrate, and so all the electrolytes coming from the acid concentrates, their values will actually slightly decrease. So potassium has gone from 2.2 to 1.99 here. In school, we learnt that Ohm's law tells us that resistance is equal to voltage upon current, and conductance is the reciprocal of resistance, so it is current divided by voltage. And the specific value, so conductance is a feature of the number of ions in solution. Charged species we know will conduct a current, and the more the valency of the ions, the greater will be the specific conductance, which is known as the conductivity, which is displayed by the machine as a function of the ionic strength of the solution. And of course, as temperature increases, conductivity will increase. This is something we looked at in the 12th standard. This is Wheatstone's bridge. So the conductivity cell of a machine is a Wheatstone's bridge. There are two fixed resistances. The variable resistance marked Rx is our conductivity cell with the dialysate, and the adjustment of the conductivity, balancing the bridge to 0, is done with the help of a potentiometer. So this is what happens. The dialysate flows in and out of the conductivity cell, and a small current is passed across it during that time. Two sensors will measure the voltage that develops in the conductivity cell, and then an analyzer will measure the ratio of current to voltage, which is the conductance, convert it into a conductivity, feed it to the microprocessor unit, convert it into a digital signal, which is then displayed by the machine. The sodium chloride in the dialysate is about 103 millimoles totally and contributes about 10.6 to the total conductivity which we set, and the sodium bicarbonate contributes about 2.5 to the conductivity. Now this looks fine. We've prescribed a sodium of 136 and the machine is saying the conductivity is 13.6. But here it's not. We've prescribed 136 and the machine is saying the conductivity is 14.2. We've prescribed 136 and the machine is giving us a conductivity of 13.2. Why does this happen? So there could be either an over-diluted or an under-diluted concentrate prepared at the time of mixing, or there could be an error in the concentrate pumps, which will need to be recalibrated. When we looked at what happens in the lab, the electrolytes will correspond not to the prescribed sodium that we have set on the machine, but to the conductivity display, and therefore we take conductivity rather than the prescribed sodium as being the actual sodium that the dialysate contains. Unfortunately, in the Fresenius machine, if you don't get the right conductivity, there's nothing you can do about it. So we prescribed 136, the conductivity is 14.2, and there's nothing you can do about it. In Alton, the machine offers you a manual override. So here, I've prescribed sodium of 136, but the conductivity is 15. At the last step of the self-test, the machine asks me, is the standard sodium 136 correct? If I say yes, the machine will accept that a conductivity of 15 corresponds to a sodium of 136, which is not actually true. So I would choose this button which says set standard sodium, and I would change that value to 150. So then the machine asks me, is the standard sodium of 150 correct? It corresponds to the conductivity. So now I say yes. The machine then says conductivity correct? Again I say yes, and then the machine will set the conductivity limits around the value which it has accepted. This is a paper that Dr. Rajapurkar, Dr. Gang and I published about 21 years ago. There were 5 patients in the unit who after dialysis developed a very severe metabolic acidosis. And what we found was that the sodiums in the dialysate were fine, the conductivities were fine, there was no alarm, but there was almost no bicarbonate in the dialysate. So it was between 6 and 12 millimoles per liter, and there was no alarm. So what had happened in these machines was, there was a precipitate in the bicarbonate line, the bicarbonate did not get sucked, and because these were servo-controlled concentrate pumps, the machine drew in more acid concentrate and delivered a dialysate with the right sodium, the right conductivity, but very little bicarbonate. And when we published this, there were a lot of people who got very upset, and the company told us there is nothing better that can be done. But there was. 8 years before this incident, the Alton people had already come up with this. The Alton machine measures the acid concentrates conductivity separately, it's 9.4, and the alarm limits are set between 7.6 and 10.6. The bicarbonate separately, 4.1, and the final conductivity, which should be between 12.8 and 14.2. So 3 conductivity probes in the Alton ensure that the dialysate will always have enough of both the A and the B part. If you have the Fresenius system, the 5008, the 5008 has 6 conductivity probes. So it measures the conductivity of the incoming water, the undiluted concentrates, the dialysate being delivered to the dialyzer, and the dialysate that is going to drain. But you can have the best of conductivity probes, and you can still have things like this happening. So the internal presets of these machines allow a machine to have a sodium of between 10, that conductivity of 10, that's a sodium of 100, to a sodium of 170, and a bicarbonate of between 10 and 80 millimoles per liter. So a machine using these sets could have a sodium of about 120 and no bicarbonate, or just about 10 millimoles of bicarbonate. Or this, it allows a sodium of between 130 to 200, and 50 to 160 millimoles of that could come from the acid concentrate. So imagine you set a sodium of 140, it could all come from acid concentrate. This machine will not alarm even if there's no bicarbonate coming in. So what is conductivity? It's an important safety tool during the treatment, but it's not a sodium or bicarbonate detector, and it's not a guarantee of dialysate safety. So if the conductivity or the temperature are wrong, the machine needs to bypass the dialysate to the drain rather than send it to the dialyzer. And normally, this bypass valve will open and bypass it, and the machine will display on the screen that the machine is in bypass. It will also be accompanied by an audible and a visual alarm, and it can also be done manually when we want to. However, in most cases, we have to take the machine's word that the dialysate has been bypassed. If the bypass valve is dysfunctional, the display will still say machine in bypass. The exception again is Alton's UltraTouch, which has 2 flow sensors on the bypass path. If the machine, when in bypass, does not detect dialysate in the bypass line, it will shut down automatically. Finally, we have to do ultrafiltration. The most common system for doing ultrafiltration today is the volumetric system, a balancing chamber. In the Gambro AK series, there is flow control, and as we saw from most of this morning, the CRRT machines have a gravimetric control. In the balancing system, we have a fresh dialysate which must be balanced by an equal volume of spent dialysate. This is what the balancing chamber of the Fresenius 4008 looks like. It has 8 valves, 4 on the inlet side and 4 on the outlet side, and the chamber is divided into 4 parts. There is a rigid partition here at the center, and there is a diaphragm which moves and divides each chamber into 2 parts. Now, this is what the diaphragm looks like. This is the Alton's UltraTouch system. The chamber is a bit bigger. It's 120 ml as opposed to 4008 where it's 30 ml. And this is the diaphragm which moves, and so at any given time, the diaphragm ensures that while one side is discharging fresh dialysate to the dialyzer, the other side is filling with fresh dialysate from the mixing chamber. In the next stroke of the cycle, the fresh dialysate which has come from the mixing chamber goes to the dialyzer, and spent dialysate from the dialyzer will come back to the chamber. So, at the next stroke of the pump will never happen unless the chamber is balanced, unless an equal volume of fresh dialysate has been delivered to the dialyzer and come back from the dialyzer, the machine will not move to the next stroke of the pump. Now, while this is happening, the ultrafiltration pump, before the dialysate reaches the dialyzer, removes a preset volume, and because this is a closed loop, then the only way that that volume can come back is across the dialyzer from the blood water. So, the ultrafiltration pump along with the balancing chamber ensures the required amount of ultrafiltration. This is the ultrafiltration pump on the 4008, and through this T connection, as the dialysate flows past, it removes a preset volume. In the Gambro system, it is a simpler system. It has an inflow dialysate pump and an outflow pump with flow sensors. The flow sensors ensure that the inflow pump is kept at a slightly lower speed than the outflow, which takes care of ultrafiltration. And this is the patent that Gambro put out, the EP, this is the US Patent Office patent, which shows the loop. These are the flow sensors, these are the dialysate flow pumps, this is the analyzer, and this is the effector. So, we've had a long discussion about transmembrane pressure in the CRRT machine, and it means a lot to us there. Now, Dr. Manisha and other seniors will remember the days when there were no volumetric balancing chambers. When we started doing dialysis, we had to adjust the dialysate pressure with a knob and a gearhead on the machine. And with the Drake-Willock 480 machine, if the water pressure suddenly increased or decreased, the dialysate flow would change, the dialysate pressure would change. So, there was no way you could ensure the ultrafiltration that you had set, and there was no transmembrane pressure calculation. Today, all the machines display transmembrane pressure, but it's not accurate. In this situation here, I have shown you the actual transmembrane pressure is 0, but because of the number of sensors, the Fresenius 4008 will display the transmembrane pressure as -40, the Baxter Tina will display -60, and the Gambro will display -50, all of which are wrong, but because there's a volumetric balancing chamber, it doesn't really matter. We heard a talk about the blood leak detector. So, this is the blood leak detector from my Alton machine. Here it is at the back. I've removed the lid. This green light over here is transmitted to a photoelectric cell on the opposite side of the chamber, and the spent dialysate enters from the base of the chamber and flows out through the top over here. Now, what happens is, as long as the dialysate fluid is clear, the light will pass through and be detected on this side by this photoelectric cell. If there are red blood cells, green and red are complementary colors. So, the RBCs will absorb the green, some of the green light, and it will scatter the rest, so that the light reaching the photoelectric cell is attenuated, and this gives a blood leak alarm. Now, what was said this morning is that if you have a dirty chamber, that's what will you have to clean that. So, if precipitates form on the photoelectric cell over here, they will obscure the light from reaching the photoelectric cell, and that will give a false blood leak alarm. My last bit is about machine safety. So, a truly machine should be fail-safe. That is, single fault dysfunction should be picked up, and a truly fail-safe device should not allow us to override it either manually or by an electronic signal. It's done with the help of redundancy and watchdog circuitry. The watchdog test is what the machine tests when we first put it on. A safe mode of operation means the patient should be isolated from an unsafe machine. It stops the blood pump, clamps the line, preventing blood which could be potentially dangerous from returning to the patient. If we are to do this, the self-test in which the machine tests its safety system should never ever be bypassed. The guidelines say alarm should be visible from at least 2 meters and about 70 decibels. I say the alarm should be so irritating that you cannot ignore it. You are forced to go and deal with the alarm condition. And so you would never want to see this message on your machine. It says test override and the test lamp is flashing. The reason it has happened is this. On the circuit board 632, the engineer has bypassed the self-test by putting this dip switch number 3 into the on position, and he has forgotten to remove it. So this means that the self-test and therefore all safety is no longer guaranteed when the self-test is bypassed, because none of the alarm systems will be tested. If I put it back into the off position, now the machine's self-test cannot be bypassed. It will have to go through the test. So I keep checking this from time to time. So to summarize, dialysis machines have made tremendous advances over the years, but there is still a potential for errors, and as they say, eternal vigilance is the price of peace. A lot about machines from many people over the years, mainly all of these. Our unit started with this dialysis machine 54 years ago, the Travanol. When I started in 1995, I used to use this one, and today we are here. But we are only doing dialysis at all because of this man and this machine. Thank you.
So thank you, Dr. Lobo. So be happy that if Dr. Lobo is not your examiner. So I'm sure many of us won't pass. So I think this much depth of knowledge may not be needed for all, but you have understood what works behind the machine, which we never even bother to look at. In fact, we don't even look at the face of the machine. Many of us, how many hours a machine has run, we are not even aware of that. And I mean, it's a very sorry state of affairs, but this is the depth of knowledge we should have, because hemodialysis, ladies and gentlemen, is the bread and butter of nephrologists. And if you don't want the dialysis company people to fool you, the dialysis technicians to fool you, at least some basics should be very, very clear. So, sir, when we joined, at least I was with Dr. Girish, sir, and we had 72 machines at that time, 72, 73.
Yeah.
So they were little bit, I mean, we could open C and all those things, and we used to do it. Then came the era of volume controlled, and then, I mean, what I aimed, it's not being an engineer at all, at least understanding what the display shows and what does it mean and all those things. So I would like to ask you a question, like if I were to start my own dialysis unit, or for the students who would like to do it, there are so many machines available. So what do you think, which machine would you think is the easiest to handle and is, I mean, is safe for the patient? Because so many things can go wrong. There are methods to bypass the alarms, which many of the clever technicians do.
Know how to do, absolutely.
So, yeah, so...
And if you, as what you said, if you don't want, if you don't know the machine, the company engineers and your technicians will get together to fool you.
So, so out of so many machines available, which one would you go for? I'm sure the company people are not there here, so you can answer that. Or maybe if they are there, so tell me if machines fine, each has its pluses and minuses. So at least we should know them. So
unfortunately, the Althin is no longer available. So Althin had probably the most safety devices to make dialysis safe, but ever since Baxter took over Althin, they closed down that set of machines. They have taken some of the features of the old Althin machines and put them into the AK98. So AK98 has good safety. Fresenius 4008 is a robust, easy to use machine, very user friendly and reasonable safety. I am not at all satisfied with the safety of machines like Nipro. I've had an experience on more than one occasion of errors. I also think that they have allowed too much of bypassing. So the first tenet, maybe the reason is that Europe and America are far more strict about patient safety. So machines manufactured in Europe and America, India is not manufacturing machines as yet. There's only one, Renalix, Dr. Lloyd's machine. I have no experience with that whatsoever. But Europe and America are extremely particular, so machines manufactured there. B. Brown machines, again, the Secura was a good machine, but in our part of the country, service from B. Brown was not good. So when you're buying a machine, make sure you get a service backup as well. So Fresenius probably has the best presence across India for service and spares, and it's a reasonably good machine. 5008 is a great machine if you can afford it, but it may be too wasteful to be using a machine which costs 14 lakhs or 12 lakhs only for pure hemodialysis. It's great if you want to do hemodiafiltration. So 4008S is a good compromise between ease of use, safety, and reliable, fairly robust. The only thing that I have with 4008 is the carbon brushes. After 18,000 to 22,000 hours, you had to change the carbon brushes. Now Fresenius is not supplying the carbon brushes. They charge you 7,000 rupees and change the motors. So I found a manufacturer in India who makes similar carbon brushes. We change them ourselves. So but yeah, so they've been telling us for some time that we are going to come with brushless motors for it. Their 5008 has brushless motors. The Alton machines have brushless motors. I've been using Alton machines for 20 years, no problems with the pumps. So brushless motors have that. And so the only defect of the 4008 is probably brushed motors, but otherwise it's a reasonably good machine. And you need to know about the preventive maintenance of it. So what you need to do once a week is perhaps to get out the Hansen connectors and put them in warm water with a drop or two of citrosterol, because some precipitates will form in the Hansen connectors, and that may not be cleaned out by a disinfection cycle. You need to check the degassing filter and the sieve filters every week. You need to give the machine a bleach clean from the front supplied menu once a week. So these are the maintenance points about lengthening the life and the performance of the machine, which need to be followed. I don't have a great deal of experience, as I said, with B. Brown. In the south, in this part of the country, I believe their service is good. In the west, the service is poor, so we gave up B. Brown machines for that reason.
So it would be a good service if you were to bring out a paper with these, the pluses and minuses, like the key points for the not so tech savvy nephrologists to understand. So that would be good.
So my colleague Dr. Chakurkar is organizing, he does it every year, 2 weeks from now, 28 and 29, a program called Dialysis Beyond Textbooks, which consists of only practical aspects of dialysis. So if anyone's interested, they're welcome to come over to KEM for that. But yeah, I think it needs to. There are some of our videos from last year's proceeding are on the KEM YouTube channel about the machines, about water treatment. So we've got those out.
But you have made the explanation very easy. It's really nice. I just wanted to ask you, have you any experience with single needle dialysis?
Yeah, the Fresenius 4008 has the single needle function. We've used it. You need a Y connection, which is available. If you don't, you can take the ones from the Prismaflex sets, sterilize them by ETO or by radiation and use them, and you can set the single needle click-clack function on the machine. It works. It delivers a slightly lower KT by V, which you can get over by increasing the length of the session. So yeah, it's a good, it works reasonably well.
Thank you.
Thank you, sir. Again, it's a mesmerizing, talk. And whenever I listen to you, I mean, it's amazing. Forget about the students. I have to question myself whether I am a nephrologist. So much
as Dr. Manisha
technicalities
said,
you go into
this
the details.
this depth is not required. We had to for a long time, because our service engineers had to come from Mumbai to Pune, so we learnt to service the machine in simple terms ourselves. Now Fresenius in their 5008 has made that impossible. Even if you open the machine, you cannot do fault finding unless you have a service card. So until you put the service card into it, you cannot do fault finding. Yes. But in the oldest generation of machines, it was possible.
So I mean, the purpose of putting your talk is like, we wanted to, make our students realize that is the, the depth we can, as a nephrologist, we can go into and learn about
because
the dialysis machines.
Many will run their own dialysis units. Some of you may be in cities where it will take the time, or towns where it will take the technician a day or two to reach for servicing. So then some of the basic things at least is worth knowing.
And as you said, Europeans, they have their own, the protocols of having a safety and all these things. And with, experience, I think we can come up with, Indian manufacturer with you being the leader with so much of knowledge in dialysis machines.
Yeah. The next step will be to find a machine that doesn't guzzle so much water. One dialysis session takes about 300 liters of water. 120 liters of dialysate. To produce that, the RO has rejected 50%. And then you have to disinfect the machine after that. So about 300 liters of water is what we waste on a dialysis session.
So when we come up with a more user-friendly, I think one of the things is the sorbent systems have not come to India as yet. When they come, it's possible to do dialysis with 6 to 10 liters of water.
So new motto would be, apart from green dialysis, how to harness the reject water and all that, green dialysis machine now,
Machines, yeah.
which will not use so much of water. So really, thank you. I mean, excellent presentation. Any questions from the?
Because actually the dialysis become 95% of ESRD patients need dialysis. Like they are serviced by dialysis only. Like transplant and CAPD may be serving around 5%, but 95% of the people with the end-stage renal disease are being served by the dialysis. That is actually the strength of dialysis. Now it is spread across the districts also, districts and subjects also. The dialysis is being spread, and people are being treated at peripheral levels also. So apart from the safety features what you enumerated in the machine, sir, can you just elaborate on how to disinfect the machine? Because actually the majority of the people are not having any problem because of the ABD malfunction, like arterial blood, the blood gas the malfunction or any other thing, but majority of them they may acquire some other infections which are in a deleterious in the long term, like hepatitis C. So to prevent that and any other bacterial infection also, if at all we are not disinfecting the machine properly, because the load of the on a single machine is very high. Like people are doing 5 sessions of dialysis in a single machine.
Yeah.
So inter-dialysis, actually what are the precautions that we need to take? How to disinfect a machine? Can you just elaborate so that actually this can be a protocol where we can improve the quality?
So the current generation of machines, especially from Fresenius and Gambro, have got inbuilt disinfection programs. Fresenius again has very user-friendly programs. You connect a can of Citrosteril, which is the disinfectant supplied by Fresenius. It's a mix of citric acid, oxalic acid and maleic acid at the back of the machine. Now what's heated citric acid is a good antibacterial agent. And in addition, what citrate does and hot water is to dissolve crystals of calcium carbonate. Well, if your machine has been going into frequent flow alarms during the treatment, or it has had frequent stops in the hydraulic unit, then as long as it keeps moving, calcium does not precipitate with sodium bicarbonate. But when there is stagnation in the machine, then the calcium and carbonate will form a precipitate, that is chalk, the chalk which we write with. And you know how insoluble that is. So once that forms inside the machine, it will typically block your endotoxin filter, your sieve filters, your degassing filters, and maybe even the solenoid valves and sometimes the gear heads. So it's necessary in such a situation to do a heated citrosterol or citric acid. Gambro advises us to use 20% citric acid, which you can make by dissolving 20 grams in 100 ml of water, and use that as the disinfectant. If you're using Fresenius, Citrosteril, if you're using the other machines, a solution of citric acid along with heat. Even the earlier generations like Alton, which are about more than 20 years old, those machines also have hot disinfection program. And heat is one of the best things for dealing with bacteria. Bacteria, if they grow in the hydraulics of the machine, may not cross the dialyzer. But once a biofilm forms, it's very difficult to get rid of, and every time there's a stagnation, it will release endotoxin. And that endotoxin can cross the dialyzer and give you rigors on the dialysis. So that's the problem with hydraulic. And so there have been situations where a machine's hydraulics have to be completely abandoned because you can't get rid of a biofilm that has actually formed. In addition, that some amount of protein precipitates and things may form, and bacteria themselves will produce a slime layer. So the company recommends that once a week we should do a front supplied cleaning with hypochlorite. So there's again a built-in program. The machine will rinse part of the time with water. It will take in hypochlorite. It will keep the hypochlorite circulating in the hydraulics for about 10 minutes, I think 7 minutes to 10 minutes, and then it will wash it out again. If you don't have a built-in program as in the one generation earlier machines, none of you will buy them, but those units which still have them, then you have to develop your own protocols, which should include heat, which should include citric acid at least once a day to decalcify the machine, and at least once in the week with a stronger germicide, either hypochlorite or peracetic acid. So that's the disinfection protocols that I think are a minimum.
Session to other session, like one patient is getting dialysis.
At least a rinse. In fact, the biggest problem that happened during COVID was when we would take machines into COVID areas and nobody wanted to be there. So the technician, immediately the thing was over,
he did something, they used to do something, and other units began to phone me as well about this, that suddenly, you know, our machines are giving flow alarms, we are changing the diasef every week. The reason is that if you switch off a machine without rinsing it, even for a few minutes, with the full conductivity in the operating range, a calcium carbonate precipitate will form. So all I needed to do in that sense was to insist the minimum you must do is to rinse a machine between two treatments. The rinse cycle of the Fresenius machine is about 16 minutes. A hot disinfection is 35 minutes. So in busy units like you are saying, they may not be able to do hot disinfection, but at least a rinse should be done. Ideally, if you can do a hot disinfection after each shift, it's great. But at least a rinse after each shift and a once a day hot disinfection cycle is